All right. I think we are all good. Uh, do see that I am having trouble seeing the notes section in my thing. So, anyway, good. Hi, everyone. Welcome to my basement where we're having our office hours. I see there's a few people on. So, welcome. I do see that there are, I don't have the notes section on my window here. So, I think actually the best thing to do is if you have a question, just send me an email. My email is aawest.astro@gmail.com. Okay. Again, aawest.astro@gmail.com. Okay. So if you have a question, send it to me. A bunch of people have already sent me questions and I will go over them. And if you have more, send them in. Oh, looks like I'm losing people. That's fine. Anyway, some of you I know are going to watch this afterwards. Okay, so the way this works is I will go over questions. As you have additional ones, just send them in and we will go from there. Okay, so let's start. The first one that lots of people had questions about was question 8 on the homework. So I decided that would be a really good one to start. And I don't want to spend this whole hour like answering all of the homework questions, although I'm happy to go over all of them and give you hints and things like that. But question 8 is one that it seems like lots of people have sent in questions about either for the office hours or have talked to me about separately. And so I thought it would be really good to actually go over question 8 on the homework. And this is the one where you actually have a table of planetary data. I think actually last year on the exam, um, we actually gave students something like this. That doesn't mean it's going to be on this year's exam, but last year there was something similar that we had you a kind of a table of data and you had to answer a bunch of questions about it. So let's go through these and I'll kind of help you understand what I was thinking and what I was expecting that you would do. Okay, so first thing to do, I guess, is just let's look at all of the worlds, make sure we understand all the pieces of information. So, of course, there's the planet name, the density of each world. The density is a measure of the mass over the volume, and that just tells us kind of what it's made of. And there were 4 main densities that I expect that you know, and those are ice, which is 0.9 grams per cubic centimeter, water, which is 1, rock, which I said you should know is about 3, and iron, which is just under 8, 7.9 grams per cubic centimeter. So, before you even look at any of the questions, your brain should be like thinking, okay, what are these worlds made of? And of course, that is question B. But, if you just look at Luke, you should say, okay, well, Luke is 6.2. Well, that's greater than rock, but it's less than iron, right? So it can't just be iron because that would be 7.9. It can't just be rock because that would be 3. And so it's got to be something in the middle. So, for example, Luke is made of a little bit of rock and probably a lot of iron. But if you just said something like rock and iron, great. That sounds good. When we get to Leia, it's really the same thing, right? It's a mixture of rock and iron. When you get 5.6 grams per cubic centimeter, you have some kind of mix of rock and iron. For those of you who are just joining us, because I see a bunch of people several people just joined, I can't see the chat window. So if you're writing comments, I'm not seeing that in my live display. I just see like the YouTube studio display. So if you have questions, instead of writing them to the YouTube comments or chat window, can you please send them to my email at aawest.astro@gmail.com. So I will answer any questions. And remember, anything's fair game. Some of the ones I'm going to go over are like things from the beginning of the universe. So, okay. So Leia, 5.6 grams per cubic centimeter. Hopefully you look at that and you say, okay, also some rock mix of rock and iron. Again, rock is 3, iron is 7.9. That has somewhere in the middle. And this one, Leia, of course, has more rock than iron because 5.6 is lower than 6.2. Han is 0.9 grams per cubic centimeter. So hopefully you're like, okay, that could be just ice. That's exactly a number that you had in your brain. Perfect. And Lando is 2.3. So again, that is too small to be just rock, because rock is 3. And it's too much to be just ice or water, which are zero point 0.9 or 1. So that's some combination of rock and ice or rock and water. Any of those would be totally acceptable. And then Anakin, of course, is the blank world in that column. And so this is one where you kind of have to figure out what's happening here. So you see that the surface composition is rocky, right? That means it looks rocky from the surface when we look at it. It has a moment of inertia of 0.39, so quite close to 0.4. Remember that the moment of inertia factor, all that I expect that you know is that if you have the moment of inertia factor is 0.4, that means it is uniformly distributed, right? Remember, that doesn't mean that it's all the same material. It could be all the same material, or it could be, a mix of different materials, but distributed throughout, right? And that's as opposed to where a world like the Earth, where you have the iron has when the world differentiated, if you remember that term, the iron sunk to the center and the rock stayed on the outside. So that world, like the Earth, has a moment of inertia less than 0.4 because there's denser material at the center, less dense material on the outside. That's really all I care that you know. If it's larger than 0.4, it's the opposite. You would have less dense material on the inside and denser material on the outside. But we don't see that in planetary geology or planetary astronomy because of the process of differentiation, where when the worlds are hot and molten, the dense material sinks to the center, and that's where you get it. And so you get moment of inertia factors either at 0.4 if no differentiation has occurred, and you have a nice, good mixing of things, or if the world is the same material, or we get less than 0.4. So when I look at Anakin, I see it's very close to 0.4. And it's a rocky surface. It's not a mix of things. It's not like chunks of rock and iron and ice. It's just rocky. So I think a really good guess for Anakin would be something made of rock. I mean, you could make arguments either way, but I would say something around 3 grams per cubic centimeter would be an awesome guess for Anakin, because it's a rocky surface. It's very close to evenly distributed. And so that's how I would arrive at that. For surface composition of of these worlds, this is kind of all this is like what you see. So if you were to take an image of this world, if you were to fly a probe and go look at Luke, what would you see on the surface? That's what I'm trying to ask when I look at that. And so when you see on the surface of Luke, you see that it's remember, Luke is some combination of rock and iron with a moment of inertia factor of 0.4. Okay, so we should take pause. So it's made of both rock and iron, but that rock and iron is evenly distributed throughout. So the iron has not sunk to the center, or else you would have a moment of inertia factor much less than 0.4. So I would say for the surface composition, when you look out at Luke, you probably see a surface that's some mix of rock and iron. The only way you're going to get a moment of inertia factor of 0.4 and a density of 6.2. All right. Let's see. What else do we have to know? Han surface composition. So here again, you have a density of zero point 0.9, we said that means that it's made of ice. It has a moment of inertia factor of zero point 0.4, which means evenly distributed, which means in this case, probably it's all made of the same material, which is ice. And so I would say the surface composition is probably icy. And what's the last blank? I guess it's not a blank, it's a question mark. That's a typo on my part. So let's see, that's Lando's moment of inertia factor. And I would say moment of inertia factor. So Lando is a density of 2.3. It has surface composition that looks like ice, but we knew that based on its density that it's some combination of probably ice and rock. So it must have a moment of inertia factor of less than 0.4. So if you're worried about, okay, well, is it 0.2? Is it 0.3? All I care in this case is it's less than 0.4. So, I would just plug in something like 0.3 or 0.35. I mean, again, as long as it's not exactly 0.4 or greater than 0.4, all I want you to know to demonstrate is that that if it's a mix of rock and ice, and there's ice all over the surface, that means the rock probably sunk to the center, and so it must have a moment of inertia less than 0.4. Okay, so that is the 4 blank questions. I think we covered what every world is made of, which is part B. Part C, I think we actually also just covered. How would you describe the distribution of material in each world? We did not do part D yet, which world is most likely to be geologically active longest, and why? So, I of course made this star exactly like the sun in every way. So in terms of its age and its size and its mass and its temperature and everything. But we saw in class that the if these are all terrestrial worlds, which did I tell you that? No one's actually asked me that question, but I assume that they're all terrestrial world. The largest is only 2 times the size of Earth. So really hard to make a Jupiter size or big massive gas giant or ice giant that's 2 times the size of the Earth. So I assumed all of them are worlds that you can walk on. So for a radius of 2 Earths, remember that I told you that for terrestrial worlds, the size actually determines, for the most part, how long they stay geologically active. And we think that's because, remember, the radioactive elements in the Earth, it's mostly potassium, thorium, and uranium. They are, deep inside, really mostly in the mantle. And so the bigger the world you have, the more volume and the more of those radioactive elements you have. But also, it actually turns out that, the more rock you have, the harder it is for that heat to kind of get out. You insulate that rock pretty well, that planet pretty well. And so the larger the world tends to be geologically active the longest. So in this case, I would just look at the sizes and I would say, oh, Anakin's the biggest. It stays geologically active the longest. Okay. Now on to F. E. If all worlds are terrestrial and you can stand on them, approximate with numbers how far of them are from your host star. Woo! All right, so this one, what I really care most about is 2 things. One, and they're all having to do with the condensation sequence. Remembering that and when you're close to the star, you can form worlds with things like rock and iron. And as you go farther away, you start forming worlds with things like ice and even different types of ice, not just water ice, but as you get farther away, it ends up being like methane ice and ammonia ice. And we saw that around a star like our sun, that transition happens at around 3 astronomical units. And that we also saw a trend with distance and density. So as you were closest to the star, you formed denser terrestrial worlds. And as you went farther and farther away from the star, the density of those terrestrial worlds decreases. And that's basically the same thing. It's that closer to the star, the denser materials can condense to form planets. And as you get farther away, you now have access to less dense material like ice. Iron is very dense. You can form it close to the star. Rock is a little less dense. Form it, still close to the star, but maybe not as close as, the more iron-rich worlds. And then as you start adding ice, the density of your worlds drop as you get farther away from the star. So the two things that are really key to look at to answer this question are, one, you need to put the worlds in order of density. So Luke certainly is the closest world to the star, and Han is the farthest. Luke has the highest density, Han has the lowest, and you need to fill in everything in between. With Anakin being, we said, probably mostly rock, so he falls between Leia and Lando in that order. In terms of the exact numbers, the only thing I care about is that you assign Lando and Han, which we said are made of either rock and ice in Lando's case, or just ice in Han's case. Those need to be assigned beyond the frost line, right? Like those cannot form inside 3 AU. So if you say Lando's at 2 AU, you're not going to get credit for that. And so you need to assign those outside of the frost line. So again, I don't care that you know exactly that Lando needs to be at, 4.5 AU or whatever. Like as long as it's past 3, done. You did your job. And same with Han. And conversely, with the interior worlds, with Luke, with Leia, and an Anakin, you better assign distances to those all inside of 3 AU, because those are all worlds that don't have access to ice to build their worlds. Their main densities are made up of rock and iron, or just rock in the case of Anakin. So hopefully that helps you with that one. I really like, that's a new part of the question this year. I really like that. Okay. On your way out of the system, you notice there's a Jupiter-sized planet orbiting within 0.05 AU of the star. Based on what you know about planet formation, why is this odd? How did it get there? Okay, so this is basically a hot Jupiter, like we talked about. The very first exoplanets that were identified were exactly this. In fact, the very first one was actually at 0.05 AU from its star. I picked that kind of on purpose, and was actually a planet much larger, much more massive at least than Jupiter. So it was very easy to detect the wobble from the star. But again, astronomers were baffled because we know the only way we know to build worlds as big as Jupiter, remember, is to start with ice, water, or rock and iron. So you have to actually have rock, iron, and ice to build up a big enough world to actually then hold on to the atmosphere. Some of the stuff I started introducing today will make this actually even more clear. It turns out that you need that base of a giant world of rock, iron, and ice, and then it has enough gravity to hold on to like the hydrogen and helium. Remember, we said Earth doesn't have enough gravity to hold on to hydrogen and helium. Well, if you made Earth, 10, 15 times more massive, it would have enough gravity to hold on to hydrogen and helium. And that's what we think happened with Jupiter. And the only way it got so much more massive is by incorporating ice into the rock and iron. And that couldn't do that close to the star. Just the water was all vapor. There's no way it could condense to form a planet. And so what we think happened is, first of all, that's why it's odd, because we don't think you'd form a ginormous planet that close to the star. And we think what happened is those planets formed beyond the frost line and then migrated in to the close distance, which actually we're able to simulate that happened. So it sounds like funny and far-fetched, but we're actually really we see that happens naturally in gravitational simulations as these planets interact with their disk. Okay, so that is all of problem 8. I've essentially given you problem 8. And I will give you one future hint. Now, I'm not going to promise that something like this is going to be on the exam, but let me just say, for those of you who either are watching live or are going to watch this after the fact, you could imagine a scenario where I give you something very similar on the exam, but I add now some other things. I add how hot that world is. I add what its escape velocity is based on our initial discussion today of atmospheres. I could give you its rotation rate, which, remember, has to do with whether or not it can generate a magnetic field. So I could give you a lot more properties here. So I think as you're reviewing your questions of the day and your notes from class, think about all the other properties of worlds that we've talked about that I could add to a similar type table like this that you may or may not see on the exam. That's the hint you get for now. Okay. Again, if you are just joining me now, I cannot see the comments on YouTube because it popped me into YouTube Studio, which I do not have comments. I can't see the comments, I don't think. There's nothing I can click on here to get the comments. And so if you have a question, please email it to me at aawest.astro@gmail.com. aawest.astro@gmail.com. Please do that if you have questions, because I see there's a few more people who just joined. Okay, so I'm going to check and see if anyone wrote. No one has. All right, excellent. I will go on to the next question that people wrote in beforehand. Let me go to it here. Okay. The next question is a quite esoteric one. So see, this is things you can ask. Is space expanding in all directions and evenly? Cool. Yes, the answer is yes, it is. It is expanding in all directions and evenly. Yes, I think the answer to that is absolutely, we think. In everywhere we look, whether we look this way or that way or that way or that way, we see galaxies moving away from us. And they all move away from us faster the farther we look away. So we all did that in class. That was the Hubble's law thing. And I showed you data from kind of like the most modern Hubble law, which actually showed that when we look even further away, it actually looks like those galaxies aren't moving as fast as they would have been if it followed a nice straight line. It looked something like here. I brought a whiteboard. Let me look at myself while I do this. So if I have something that looks like this is the velocity, I'm going to say v. There. You can read it now. And this is the distance d. Okay, we saw that Hubble's law was something like this. It was a nice straight line. We did that when we did the California example. As you go farther away, which is this direction, galaxies are moving away faster, and it was linear. In fact, in a uniformly expanding universe, just like when I did a uniformly expanding California, the farther you went away, the faster they went. Okay, excellent. So, but in reality, what we actually see is that it looks something like this, or it doesn't quite bend over like that. But as you go farther away, the galaxies look like they are moving slower than the normal Hubble law would give. And this is really far away. This is like at billions of light years away. Once you get that far, you see this trend. And what this actually tells us that the universe is actually accelerating, because when we look back, the galaxies look like they're moving much slower back here than we would expect. And remember, when you look billions of light years away, you're looking billions of years into the past. So if the galaxies are moving slower than we expect in the past, it means that the universe would have to have accelerated to look like what it looks like today. So Hubble's law has essentially like gotten faster because the universe's expansion has accelerated over time. Crazy, huh? Okay, so super crazy question. But so did I fully answer it? Is the question. Expanding in all directions and evenly. Yes. So everything we think is that this is happening. Again, if we look that way or that way or that way, we get the same result. So it's even. It's in all directions. Is expanding evenly. The bigger question is, is this happen? Like, is there a limit? Is there some bound? And remember, again, we are stopped. We have to stop ourselves from even being able. I mean, it's a great question to ask in our brains, but we can't scientifically answer that because we're limited by time, right? So we can only look so far away because we have to wait the billions and billions of years it takes for that light to come from the edge of what our observable universe is to us here today. All right. So if the universe does have some finite size, which sure it might, but it could be infinite as well. Who knows? I guess the answer to that is we actually won't ever know because we are limited in our own observable universe. So in our own observable universe is spherical, it is even, it's the same, it's homogeneous in terms of at least uniformly distributed in every direction. The same principles like the Hubble flow or Hubble law apply in every direction. But beyond, that time domain that we can see, we don't know. We don't know anything about that. And barring crazy physics or crazy travel that's beyond what we understand or comprehend right now, we won't for a very long time, if ever. Wow, crazy. All right. I saw that someone wrote a question in. Sweet. Does Hubble law prove that the universe is expanding uniformly? Well, yes and no. So the no part is, I hope one takeaway that everyone takes away from this class is that, like, science does not prove anything. So I know that's just the language that the email said, and it's probably quickly written and everything. But I really hope that that's like a key piece of this class that you get from not just me, my portion, but like other people's, is that science is an evidence-based enterprise that is constantly changing. All right. We propose ideas, we test them, and then sometimes they pass those tests, and sometimes they fail those tests. Science can disprove things, but it can actually never prove something. It can show huge amounts of evidence for things, but it can never prove it. So, slight pet peeve on that word. But other than that, the Hubble law is the main evidence for the the uniform expansion of the universe. In fact, that it is from Hubble's initial results that for the first time astronomers went from thinking, there were people who thought that maybe the universe was expanding or maybe it was contracting or, that maybe it wasn't static. But I would say the most popular idea, this was now 100 years ago, a little over 100 years ago, the most popular idea was that the universe was static, that it didn't move, that, galaxies were where they were, they hung out, that was that, right? Like maybe there was some movement due to gravity and things like that, but other than that, no way, static universe. And so what Hubble's data showed was that there was strong evidence for a uniform expansion of the universe. I think that answers the question that I just got. Yeah. Oh, how does it show that it's expanding uniformly? Oh, I'm sorry. I misread the question. Well, first of all, it doesn't prove. But how does it? So this was the California example. Maybe I'll go through that one more time, just as an example. Let me wipe this off. Let me find something real quick. I don't want to use my nice hat. 1 second. All right. Well, I didn't anticipate that. I should have. Here, we'll do it on the other part of this. So let me choose a different state. I guess one of the homework assignments really asks you to do this, right? It asks you to imagine that you have are expanding in an expanding universe. Let's see. This is question number 4. Really asks you to assume that you're in an uniformly expanding universe and to look at different objects. That's really like what I did with the California example, right? But let's just do it like with, I don't know, like a square or something, right? So if you've got a square right here, okay, and you have point A and point B over here, and you're sitting right here. Is that too small? That's way too small, dude. Okay, hold on. Make a bigger square. Bigger square. I'm gonna sit down here in this point right here, okay? And I'm gonna make point A be right here and point B be way over here. And we'll pretend that point A is point B is 2 units away from me, and point A is 1 unit from me. Okay, so that's my universe. All right, I'm sitting here in the universe, the square universe, and now all of a sudden my square uniformly expands. So now let's do just a factor of 2. All right, so all of a sudden my square is uniformly expanded in all dimensions. So now I'm sitting here again. A is right here, and B is up here. Hopefully everyone can see that. And now this distance is 4, and this distance is 2. Okay, hopefully that's like cool with everyone, right? Like I had a square like this. The distance to A was 1, the distance to B was 2. Here, the distance to A is 2, and the distance to B is 4. I might even be doing the homework problem for you. That's okay. If you're watching this, then shit, you get free homework. All right. So now, if you actually were sitting here and you were watching this happen, let's say that this expansion happened in 1 second. You were looking at A, you saw A go from 1 to 2 in 1 second. So it moved at 1 unit per second. Okay? So 1 unit per second. Whereas you watched B go from 2 to 4 in 1 second. So A moved at 1 unit per second, and B moved at 2 units per second. So man, B is moving faster than A, even though the universe was expanding totally uniformly. Things that were farther away were moving faster. If that still is like blah, then you need to like sit down, draw your own state, draw your own shape, and kind of figure this out. It's pretty neat. I mean, it's a pretty cool like kind of trick of even geometry. But this is what Hubble saw. He saw that galaxies farther away were moving faster, and he kind of backed this out of the geometric argument and said, "Oh, right. The only way that could happen is if we were in an expanding universe. If I was like in a square and then the square got bigger and then the square got even bigger, at each of those bigger steps, I would see the things that are farther away moving away from me faster if I'm also in that square." Okay? Cool. All right, let's go to the next one. I got a bunch now, so this is great. Someone had a question about question 7, which is the one about how the Hubble's galaxy data and the cosmic microwave background radiation support evidence of the Big Bang. Well, the Hubble data, first of all, really just it shows that the universe is expanding, and that's central to the Big Bang. In fact, I would say even more than evidence of the Big Bang, it actually probably, well, it is what like helped create the Big Bang. But that is in itself part of the Big Bang theory, is that you start with a essentially infinitely small universe. Like all that there is kind of crammed into the tiniest size, and it's super hot, and then as it expands, things cool, you begin to form atoms, you begin to form more complicated atoms, so on and so forth, and then eventually stars, galaxies, people, whatever. But that's central to that whole idea is that the universe is expanding. So the fact that we see that, right, and we continue to see that today, we actually see it even accelerating today, is direct evidence that there's at least an expansion, which is a central part of the Big Bang. Now, even more so, the cosmic microwave background radiation, which I showed you a couple times in class, that is direct evidence of the Big Bang. It's why the people who identified that the first time actually won the Nobel Prize, because their discovery was a direct prediction of the Big Bang theory. Like, to have a successful theory in science, you don't just have like an idea and then like, wow, run with it, see if it happens. To have like a real theory. Remember, theory isn't like what we say in kind of common speak, right? Like a hypothesis is an idea. That's what most people say. Oh, it's just a theory. Like they really mean it's just a hypothesis. A theory is something that actually is based in lots of facts and lots of like ideas with evidence, and where you actually make clear predictions. You say, if my idea is correct, here are 6 things that will happen. And the thing about that is, if like even one of them is wrong, the theory fails. The theory is actually disproven. All right. But the Big Bang actually lays out a bunch of different things. Obviously, I didn't have time to like go through. We took a class on like cosmology, the origin of the universe, we would actually spend at least half of the semester actually going through all the steps of the Big Bang and actually demonstrating all the things that in the 1950s and 60s, they said, if the Big Bang is correct, here are all the things that we would find. The number one thing, like the one that like was probably the biggest prediction, was that when the universe was, still expanding, it was so hot that even after you formed the first atoms, even after you formed the first, protons and electrons, and then even those formed, started forming more complicated things, the universe was so dense that you couldn't even get light through. So if there was light, which there was light, because anything with temperature gives off light. That's another thing we've learned in the class. So there was thermal energy, which gave off light in the early universe. And the universe was so dense that the light couldn't get out, right? And that's something like, hopefully everyone can understand, right? Like, you can't see the sun on some days where it's really cloudy because there's so much water vapor or condensed water in the air, it can't get through clouds, right? Same thing, right? Or there's a wall in the way. Hey, it's so dense, I can't see the light. Early universe was exactly like that. Like, you just could not get any light anywhere. And so they predicted there was a point at about 3 to 500,000 years old. So think about it. Universe is, almost 14 billion years old, when it was only about 500,000 years old. So in its infancy still, the Big Bang predicted and continues to predict that there is a point where the universe gets diffuse enough, the opposite of dense, where you can start to peek light through. And they said, if that's true, anywhere you look in the sky, you will actually see this light that's left over from the Big Bang. And that's exactly what the cosmic microwave background is. It is light that is literally started coming to us when the universe was about 500,000 years old. All right? It's when the universe, and it's the first light we ever see in the universe. You actually don't see anything beyond that because the universe was too dense for light to get through it, just like a cloudy day or something like that. So it was, this was when it was discovered in the 1960s. It was a ridiculously exciting discovery because it was like the first major piece of evidence for the Big Bang. Since then, lots of the steps have actually been found, and most of those people have won the Nobel Prize if they found it. There's one actually like outstanding one. There's actually something called the cosmic neutrino background. There's these subatomic particles called neutrinos, and the Big Bang actually predicts that there's this neutrino background everywhere. And we actually don't have instruments now that are sensitive enough to like find it. So it's not like we haven't found it and so it's failed. It's that like we don't actually have the technology to detect these neutrinos from the edge of the universe. But I guarantee you, if you want a Nobel Prize in physics, go find the cosmic neutrino background. It's like guaranteed. Whoever finds it will win the Nobel Prize. So hopefully that answers the long answer to someone's question. Let's go to the next one. All right. So let's see. Um, so someone just had a follow-up question to what I just answered in terms of I just answered the Big Bang, the cosmic microwave background question, and hopefully they were listening and got the Hubble expansion question. But they have a question about the movement in question 4, and let's just see if I actually use the exact 2 feet away. I use 2 and 4 feet to start. So what I'm really curious about people doing in question 4, this is when you have imagine that space around you is uniformly expanding. How would you be able to tell that it's uniformly expanding? So, and I tell you, in order to do that, I want you to compare an object that's 2 feet away to another that's 4 feet away, and I want you to watch those as they move. And maybe like this is worded a little confusingly. What I really want you to do is do exactly what I did on this clipboard. So when I say relative to each other, I guess maybe a better phrase, since this was written quickly, is here's the board. I want you to actually tell me relative to you, the observer. All right. So what I want you to do is tell me how is A moving away from you as that universe expands compared to how B is moving away from you as the universe expands. So think about how fast they move away from you, just like I did in this example. It's slightly different numbers, but not that different. And then compare, you'll get 2 different velocities that they're moving away from you. Compare that to their original distances from you. And I think what you'll find, I mean, you know what you should find already. You should find that the object that was farther is moving faster away from you than the object that was closer. And so, again, another example, what I'm trying to get you to do in that homework is just practice and like train your brain to think about the fact that in an expanding geometric shape, if you are at one point, the objects farther from that point are moving faster away from that point than the objects closer, even if it's uniformly expanding. Crazy, huh? Anyway, that's what I want you to think about. Hopefully that clarifies it. If it doesn't, ask me another follow-up for sure, please. Okay, so let me go on to the next one. As you guys are writing more, let's see. What do they think could have initially caused, oh man, here's a big one, the Big Bang expansion? If it was just there was a lot of mass concentrated in a very small area, wouldn't black holes also have this effect? Holy man, that's an intense question. So what was there before the Big Bang? What was the Big Bang? How did it start? Wow, what caused it? Well, I will give you the like science version, and then I'll give you maybe the more esoteric philosophy version. So first science version is that when we do the Big Bang Theory and we look at it, the Big Bang Theory has a finite beginning. It says very clearly that we cannot know, well, it doesn't explain what happens before a certain period of time. In fact, using the Big Bang Theory in kind of its most modern form, we can go back to a time that is 0.00000. I'm not going to do this. Literally 43 zeros with a 1. That many seconds since the beginning of time. Like, I'm pretty confident based on, like, again, evidence and predictions and evidence of said predictions that we can actually know what the universe looked like back to 10 to the minus 43 seconds. which is like, 0.00000001 second. So fraction of a second since the Big Bang. Turns out at that point, the physics that we know now breaks down. So it turns out like the four forces that we know, gravity, electromagnetic, weak, and strong, actually don't play nicely together at that one distance called the Planck length. So before that, we actually have no answer to the question that I was given here. Like, science does not say anything. Now, does that mean there is no answer that science will someday do? No way, man. Like, there have been lots of things, many of which we've talked about in this class, that 100 years ago, 1,000 years ago, even 30 years ago, people had no answer for, right? That doesn't mean like we need to invoke other crazy stuff. Like, all it means is that, like, at this point, we don't know the answer. So that is like the science like thing. Right now, we cannot actually answer that question. We do not have the ability or the skills or the knowledge to know what happened. The more philosophic question to kind of the beginning of it all and the Big Bang is that, like when we talk about the Big Bang, we talk about this beginning of the universe, we are literally saying the beginning of time. It's not like, the universe is in a room and there's some other time playing and it's like, okay, yeah, like at 10 o'clock, we're going to start expanding and it's going to expand into my basement here. It's going to expand to the room. No, that's not the way it works. We are talking about the beginning of space itself and the beginning of time itself, right? Like, time didn't exist before the Big Bang. So it's not like anything existed before. Space didn't exist before the Big Bang. The space is all that there is. So when there was no space, it's not like it was a tiny little dot in this room. It was all of space itself. It just happened to be a lot smaller. Things were a lot closer together than they are today. All right. So, like, you have to kind of philosophically bend your mind around that fact that when we talk about this, it's not like we're talking a balloon expanding into a room, right? Like, we're talking about all of space expanding from like really nothing. Now, how did it start? Beats me, man. Like, I think this is a totally appropriate place if you're religious to invoke like a deity, perhaps. I think, if you're not, that's fine too. I don't think you need to invoke that. Like, there certainly are laws of physics and nature that all began at that point, which are beautiful and exciting. And I still think like we will know closer to the beginning of time than we know. But will we ever know before that? I'm highly doubtful. Like, because again, it is the beginning of time. And unless time works totally differently and weirdly than we actually think it does, which it might, I don't know the answer. So that's my 2 cents weighing in on that highly esoteric question. But luckily I was saved by another one. It's question 9. Do we have to be specific about the elements that form for more massive stars, or can we just give a range of elements on the periodic table? Let me turn to question 9 here. Question 9 is the one that says, for 4 stars, one like the sun, one that's 7 more times massive than the sun, a star that's 10 times more massive than the sun, one that is 30 times more massive. And what type of elements that produce? You do not need to like give me the laundry list or be specific, other than I expect that, for a star like the sun, the only element that a star like our sun produces, I'll just give it to you, is helium, right? Our sun is not massive enough to form any other elements in its like fusion, even when it goes through the red giant phase. But if you have a much more massive star, like the one that's 7 times more massive than the sun, hint, that forms a lot more elements. Again, I don't care that you give me the whole laundry list. What I care is that you understand that's where like the bulk of the elements that really are important to us are created. And then same for a star that is 10 times or 30 times more massive than the sun. Those produce additional elements that Again, you don't need to write down the whole freaking periodic table, um, or the majority of the periodic table. Just you can just tell me like the elements more massive than blank, uh, right, or something like that. Like I don't need. What I'm looking for is that you understand that different mass stars produce different types of elements. Again, in the appreciation that when you take a deep breath of air in, when you look at the jewelry we wear, like those are coming from actually different types of stars, right? And our sun actually doesn't produce any of them. So, holy crap, right? Like you got to have more massive stars, and in some cases, very much more massive stars to have the kind of things that we have here on Earth. So, I hope that answers your question. Again, send me a follow up. I'm really sorry that the chat thing didn't work. YouTube and Google have changed this in the last year, and I did a setup, but I didn't do a trial. So hopefully it's not a pain in the butt. Again, if you're just joining me, we've got like 10 minutes. I can stay a little bit more if people still want me to answer more questions, but aawest.astro@gmail.com. Send me an email. I will answer your question online, live on air. Okay, got a couple more coming in here. Let's go to the next one while we still have time. Ooh, wow, another cool one. If all humans physically left the Earth, would the mass on the Earth change enough to shift its relationship with gravity and other planets and stars? And the answer is no. Like you could do we could do a quick order of magnitude calculation. So the Earth is what, like it's like I don't have the like mass memorized, but I have other masses memorized. So let's see. Let's look it up. Hey, I mean, this is not something I have in my brain. I actually have the size of the Earth memorized, but let's just do this. Mass of Earth in kilograms. Hey, even better. Okay, cool this out. So it is 6 times 10 to the 24 kilograms. Okay, so that's a lot. 10 to the 24. 6 times 10 to the 24. Okay, so humans, weigh anywhere between, like, right, if you're a big guy like me, you weigh 100 kilograms. A lot of you in class weigh like somewhere probably between like 40 and 70 or something like that. So, right, like let's make the math easy and say everyone's big like me and make it 100, which is like an overestimate because most people are smaller than me. Okay, so 100 kilograms times how many people are we unfortunately currently at? Like 8 billion. All right, so we're doing astronomy units. We're just going to say 10 billion. All right, so there's 10 billion humans on Earth, each weighing 100 kilograms, which is way more than there is. But this is an overestimate. So 10 to the 10 is 100 billion. I'm sorry, it's 10 billion. A billion is 10 to the 9, one with 9 zeros. 10 billion, one with 10 zeros. So times 100, that's 10 to the 12. So 1 trillion kilograms. All right, remember that the Earth is 6 times 10 to the 24. So 1 trillion kilograms, a weight overestimation for all of the humans on the Earth, is 10 trillion, which is a tiny, tiny fraction, like 1/10 to the 12th of the Earth's mass. So no, there would be zero effect on the Earth's mass. Anyway, that's a quick, fun order of a magnitude. Now I'm going to lock in my brain 6 times 10 to the 24 kilograms. All right, try not to forget that again. It's actually not one I'd use. I have to use stellar masses all the time in my research, but I don't do research on the Earth, so it's not a number I use a lot, shockingly. Anyway, cool question. All right, next one. Let's see. Is there a point where the universe would stop expanding? How can there be no limit or unlimited space? Oh, okay, another cool esoteric question. So wait, first part of that was, is there a point when the universe would stop expanding? We don't think so at this point. Again, when I when I was younger, when I was in college, the accelerating universe thing had not actually been found yet. There was some hints that maybe that was happening, but there was no like strong evidence for it. And so there was a real possibility, and we all had to learn about it, that the universe could like accelerate or expand and then just kind of coast forever, or it could actually expand and then contract. Like it could go and then contract back down. Like, and the idea there was like if you have massive objects in the universe, like galaxies and clusters of galaxies and stuff we didn't even talk about, like that there might be enough mass to actually pull space back together. And actually, you can do the math and see that if you had enough stuff, you actually would be able to do that. And so there were these like contracting universes, and it was really cool. And some of the math and geometry is really neat. But it turns out there's not enough mass. We know now in 2020, there's not enough mass to do that. So not going to happen. And there's actually not, it's probably not going to coast. In fact, it looks, for better or worse, like it's just going to accelerate forever and ever and ever and ever. And there appears to be nothing stopping it. In fact, the force, if you will, which we don't know anything about, we call dark energy, that's actually, we think is causing the accelerating universe, has this really annoying, weird property that when you expand it, it actually gets stronger. So it's what's called a negative energy density. I'll unpack what that means. When you take a balloon or a ball and you squish it down, we all know that most of the time what it wants to do is push back at you, right? So when you compress it, the force to expand actually pushes up. All right, like, and the opposite happens. If you actually could grab the ball and pull it out, it would want to pull back down. Well, that's like what happens in like normal space with like the normal pressures and densities that we deal with, like on Earth and that we breathe and in stars. This negative energy density, this dark energy, appears like in every way to be exactly the opposite of that. If you take that ball and you like expand it, it actually wants to get even bigger. And that appears to be what's happening. And every piece of evidence we have, which is not just like expanding universe, there's actually other things. Actually, the patterns in the microwave background also point to exactly that. It's not very elegant, and I don't really like the idea if you can't tell, but like I have to actually admit that the evidence is like pretty overwhelming at this point. So that's the first part of the question. Probably not going to stop expanding. How can there be no limit to space? Well, this goes to that other thing I was saying, in that like this is like space is all there is, right? So it's like a lot of us, I think, when we first hear that this the first time, we think of like a balloon expanding in a room, right? We think of like something expanding into something else, but that's not what this is. This is like all that there is. Like space is just space, right? It's not like expanding into other space. It's just space itself. So that's why people think, there may not be a limit or an edge, is because, anywhere you go in this great big wide universe, there's still space. Now, could there still be an edge? Of course there could be. And we're never going to see that edge unless our observable universe goes over the boundary of that. Remember that as time passes, we can kind of see a bigger swath of the universe. Of course, that universe, meanwhile, is expanding, accelerating, but which is problematic for that. But we are able to see a little bit more of the universe as time goes on, and the horizon that we can actually see expands. And so maybe at some point in some direction we'd see, oh wow, we're not seeing as much stuff in that direction versus this direction. There must be an edge that way, but we're not there yet. Again, everywhere we look, as far away we go, we see a uniform distribution of material. So I would say all evidence at this point points to like infinite, like no limit universe. Does that mean it actually is that? No. But I would say like that's probably the better guess at this point. Okay. Is the universe flammable? That's so awesome. Uh, for the most part, no. The biggest thing you need to be flammable is oxygen, right? Like fire is a chemical reaction that takes like usually carbon and oxygen and spits out actually water and carbon dioxide. I think that's like the basic like chemical formula if I remember my basic chemistry. And so you need oxygen is like the key thing, right? And oxygen is like crazy rare, it turns out. So there may be other pockets in the universe where you can have fire and flammable nature, but most places no, there's not enough oxygen to actually burn. I mean, I can think of like nowhere else on in our solar system where you could actually have fire. There's like a buttload of gas on Titan. I mean, Titan has like lakes and oceans and rain and clouds of gas, like ethanol and methanol, methane, ethane, like nasty shit. Like it is, but there's no oxygen there. So like you're full of gas. You could like power your spaceship if it ran on gas, although that's probably not an efficient way to power a spaceship. But like, there's no oxygen there to burn, so it's not like the whole planet's going to catch on fire. The whole world. All right, I'll do a couple more here. So send if you have one last one by email, you can send it. What existed before the universe? I don't understand how something could form out of some seemingly nothing. Well, again, this is like maybe that kind of esoteric question about uh, what happened before that Planck time, that 10 to the minus 43 seconds. And I think I already mostly answered that. Really, that like, we don't know how it all started. I mean, that's really, I don't need to beat around the bush. Like, we just don't know how it started. We do know it started, and we know it like back to like when the universe was 10 to the minus 43 seconds old. But what happened before that time or before that time? No idea. When that started, there were some laws of physics in place, like right, like the force of gravity, the electromagnetic force, the strong force which holds atoms together, is the weak force which actually governs how um, atoms decay, like the beta decay that we've talked briefly about in this class. Like that's governed by the weak force. Like those things are set. Like they are the same everywhere we look in the universe. And so that's pretty cool. Like those things started with the universe and they actually allow the universe to expand the way it does, right? Like the reason you get the universe cooling as it expands is directly due to like thermodynamics, which is a direct response of both quantum mechanics and gravity. Like there's really cool stuff that happens, like strictly from just like basic physics. Um, but how did that all start? Like, how did all the crap, like the mass and energy that makes you and me, how did it get there? No idea. How did those laws of physics get set up? No idea. They're just the way they are. Are they different? No one's asked, like, are there other universes? Sure, maybe. Are there different universes with different physics? Oh, sure, maybe. Like, not sure, like, we'll ever have the evidence to see those things. I'll wait and see if there's one last question, but because I think I actually answered everyone else's question. But I'll share at least one thing while we're waiting, and then I'll say bye if there's nothing else. One of my colleagues once got a question that was, okay, so like, what is the universe expanding into, right? Like, and I already said like we really shouldn't think of it like expanding into a room because it's all that space is. But his answer I thought was amazing, right? Is that they, he had a student or someone asked like, what is the universe expanding into? And he said, the future. Right. And like we know that's true, right? Like that's hopefully a takeaway you have from this class is that like, as the universe expands, like it actually is that light will travel to us, right, as it's coming. And so you're actually able to see farther and farther back. And that light, that extra expanded space, the light will come to the future and come to our eyes or our predecessor or precessors. The people will come after us. Wah! English is failing me at 8:30 at night after a long day. Anyway, if there's no last things, um, thank you for all your awesome questions. I hope that I helped you some with homework. Um, I encourage you to talk to the TAs. I know some of you have gone to some of their office hours. I encourage you to send me emails. Some of you have, and I owe you, some of you, some responses, which I will try to get to tonight. If not, I'll do it tomorrow. And I will do another one of these. I probably will not do one before the homework's due next week, but I will do one certainly for the next homework and certainly before the exam. I will do another one of these because I think there were enough people and enough questions. I think it was useful. So have a good night, and I'll see you guys all on Tuesday for our continuing discussion of planetary atmospheres. Have a good Valentine's Day and a good weekend. Bye.